So welcome to lecture 10. In today's lecture, we shall discuss differential cross-sections, decay rates, and scattering matrices. This is where quantum field theory meets with experiments. So let us first explain what cross-sections are. So in general, there are two ways in which quantum field theory connects with experiment. One is through cross-sections, and this is an observable in scattering experiments, and the second is through decay rates of unstable quantum particles. So first, let us discuss cross-sections. So the setting that we have is something like this. We have a bunch of particles, say over here, let's call them, say, particle type A, and they're traveling with some velocity, say VA, in that direction. And there is some, say, target particles sitting over here. So in the lab frame, the target particles can be taken to be stationary, and the target particles are called B. And suppose that the density of the particles, A particles is rho A, and the density of the target particles is rho B. And that the length of this beam is, say, LA, and the length of this beam is LB. Now, after these two groups of particles scatter, there will be end products coming out, and those end products, what happens is this happens in a particle collider, and there are in the collision chamber, around the collision chamber, there will be a lot of detectors, and those detectors will measure the charge and the mass and the energy momentum of the end products of the scattering experiment. So what we want to do is to predict a quantity from quantum field theory, which is going to be independent of the detail of the experiment that is being done. So suppose there are two different experiments involving the same type of particles A and particle B, but the density of the two particles might be different, the velocity might be different. What we want to do is that we want to predict what the experiment is, regardless of the setup, based on the fundamental physics, which is encoded in the underlying quantum field theory. So the cross-section and the differential cross-section is such a quantity. So in this setup, let's take A to be the cross-sectional area that is common to both of the particles. So A is cross-sectional area, that is common to both beams, or to both groups of particles. From elementary considerations, we can say that the number of scattering events It's going to be proportional to the density of particle A, the density of particle B, the cross-sectional area that is common to both, the length of the beam B and the length of the beam A. And the constant of proportionality is what we called the cross-section, and traditionally it's denoted by the symbol sigma. So this is called the cross-section. And the cross-section is given by the number of scattering events divided by rho A, rho B, A, LA, LB. So in other words, all the details of the experiment, such as the density of the particles, the overlap area, the length of the beams have been taken out. So it's easy to verify that the dimension of sigma is going to be that of a length squared, that is area. So it is an appropriate name. So now, if Na and Nb are the total number of particles, so if we say big Na is, say, La times the cross-sectional area times, say, rho A, and B is LBA rho B, then we can say that sigma is going to be the number of events divided by, say, Na by LAA. Of course, this is just the density. And NB, LB times A. And then there's a factor of A, LA, LB. So these guys cancel out. One of the factors of A cancel out. And then we have the number of events is going to be equal to the cross-section times NA and B divided by A. And of course, this makes it clearer that the dimension of sigma is that of area, because the left-hand side has no dimensions. Now, what is the interpretation of sigma? So sigma means that if effective area, so it's the effective area that one type of particle has in relationship to the other, and which contributes to a specific uh, result or output. And therefore, if we have more than one type of particles or more than one set of decay products that can come out of the same initial particles, then we'll have different cross sections for each of those processes. Now, the output will also vary with the momentum of the outgoing particles. So in the experiment, of course, we'll have some control over the momenta of the incoming particles. So that is, if you like, our independent variable, but then the output is going to be, in general, of particles in a range of momenta and energy. So the output, when we consider the output as a function of the range of the three momentum, that is known as the differential cross-section. So when we look at the part of the cross-section as a function of the momentum of the outgoing particle, that's what we call differential cross-section. And it's usually denoted by d sigma, and it's going to be a function of the momentum of the first output particle, say the momentum of the second output particle, and if there are n end product, n end product, then it's going to be a function of n and outgoing momentum. However, in this course, we'll be mostly interested in 2-to-2 scatterings. That is, we'll have some initial particle A and B, and then they'll go to some final particles, say C and D. So this is 2-to-2 scattering. So because of overall 4 momentum conservation, so there'll be a overall 4 momentum conservation. Okay, because of the overall 4 momentum conservation, we see that of the 3 momenta of the final particle, which has in total 6 components, so only 2 components of the final 3 momenta will be independent. And we can take these to be, say, what the angle that specifies the direction of one of the final momenta. In other words, we can think of the differential cross-section for 2-to-2 scattering as being a function of the solid angle of one of the momenta of the final product. So we can think of the differential cross-section as d sigma by d omega, where omega is the solid angle. And then the total cross-section would be a sum over all the momenta. So in this case, it would be an integral over the solid angle. So this is cross-section in brief. Now we need to figure out the quantity that we want to relate it to coming from quantum field theory. And for that, we have to turn to the scattering matrix.